Hello everyone, this is week 8, the first lecture. So, recall that in week 7 we had started with algorithms for constraint optimization, and we learnt about quadratic penalty method, right. So, and we had two major issues with quadratic penalty method. Unless the penalty is really high, by high it is like in millions, right. So, only then, so I mean we took problems which are like in 2 dimensions, right, with maybe 2 constraints or 3 constraints max, right. So, even for such problems the value of the penalty, the gamma value had to be as high as in millions, right. And the other issue was, if you recall, we we gave an example where for lower values of gamma the minimum did not exist, the minimum actually diverged to infinity, minus infinity, right. So, thus we are actually going to a new method called augmented Lagrangian method. Okay. So, let us get started, and we will actually first start with an optimization problem that has only equality constraints. Okay. So, for example, or rather I mean the general form of such a such an optimization problem is min f of x subject to j of x equal to 0 for all j equal to 1 to p. That is, we have just considered p to be 0. Oh, okay. So, I will use m here since that is what is used here. Okay. So, yeah, we have only equality constraints and no inequality constraints. So, let it be j of x equal to 0 for all j equal to 1 to m. Okay. All right. So, let me actually start by illustrating the basic difference between what we are going to have in I mean what we had in quadratic penalty method and what we are actually having in augmented Lagrangian method, right. So, if you recall, for such a problem in quadratic penalty method, we defined q of x comma gamma as f of x plus gamma into summation j of x the whole squared, right. So, this is what we defined in quadratic penalty method, and then we fixed a value of gamma and minimized q of x comma gamma, right. In augmented Lagrangian method, it is only going to be slightly different. What is it? We are going to define something called L gamma of x lambda gamma. Okay, or, since I have written gamma here, I will just write it as x of lambda, x comma lambda. Okay. So, this is going to be f of x plus summation lambda j j of x j equal to 1 to m plus gamma summation j equal to 1 to m j of x the whole squared. Okay. So, what is the difference? I mean, just by looking at the expressions in these two methods, right. So, you can see that f of x is there in both of these functions, and the penalty gamma summation j of x the whole squared is also there in both of the functions. Augmented Lagrangian method has some extra terms which is the summation of lambda j j of x. Okay. So, the first question should be, why do we add a penalty to f of x plus summation lambda j h j of x instead of adding it just to f of x, right. So, in quadratic penalty method you can recall that we added penalty only to f of x, and in augmented Lagrangian method we are actually adding it to f of x plus summation lambda j h j of x. So, why this difference? So, if you recall for constrained optimization, right, we are actually constructing a Lagrangian function, right, and differentiating that to obtain the critical points, right. So, if you recall the very old lectures from week 1, right. So, I can bring it up here for you. So, yeah, assume that you do not have the inequality constraints that are mentioned here, that are underlined, right. So, you will only have min f of x subject to h j of x equal to 0, right. So, we construct a Lagrangian. So, we have f of x plus summation mu j h j of x, and we just have the first two lines of constraints, right. Of course, the g I will not be there. Okay. So, in other words, let me let me write this down here. So, if you were to solve this problem analytically, min f of x subject to h j of x for all equal to 0 for all j equal to 1 to m, right. So, what would you do? You will construct L of x comma lambda as f of x plus summation lambda j h j of x j equal to 1 to m, okay. And you will find the gradient of L with respect to x, right, which is del f of x plus summation lambda j del h j of x j equal to 1 to m. This should be equal to 0 vector, right. And when you differentiate with respect to lambdas, so if you for example, if you differentiate with respect to lambda j, you just get h j, right. So, I can write it this way. I do not know if you have seen it this way, but nevertheless you can do this. So, that is just h j of x, and that is also equal to 0 for all j equal to. So, this implies this for all j equal to 1 to m, right. And I mean you need x and lambda that actually satisfies all of these conditions, right. So, that is how we actually find the critical point. In other words, we are not minimizing f of x. So, in an unconstrained optimization problem we actually minimize f of x, right, but here you can actually consider that we are minimizing the Lagrangian function L of x comma lambda instead of minimizing f of x. Okay. So, in that case maybe it makes more sense to add the penalty function to the Lagrangian function instead of the objective function itself, right. So, that is exactly how augmented Lagrangian method works, at least when you have only equality constraints. Okay. So, what I am saying is that, so if you recall the quadratic penalty method, we have a step where we minimize q of x comma lambda x comma gamma with respect to x, right. So, instead what we will do here is we will minimize L gamma of x comma lambda with respect to x, okay, for a fixed value of gamma and a fixed value of lambda. Okay. So, let me indicate that here. So, yeah. So, this was the quadratic penalty method algorithm, and we have this step where we actually minimize q of x comma gamma with respect to x, right. This step is going to become find x k equal to argmin x in R n L gamma of x comma lambda, okay, for fixed values of gamma and lambda. Okay. So, possibly I will just write that down. Yeah. So, yeah, the minimization step will actually become xk equals argmin x in Rn L gamma of x comma lambda, okay, for fixed values of gamma and lambda. Okay. So, that is a key difference that we have between quadratic penalty method and augmented Lagrangian method. So, you will possibly now ask is if the other steps are the same. Okay. So, let us just have a look to see if the other methods can other steps can be the same. Okay. So, yeah, so we initialize x 0, we initialize k, we initialize tolerance, and yeah, so we initialize only one value of gamma, we do not initialize a sequence as we did here, right. So, we just initialize one value of gamma, and we also initialize a value of lambda. Okay. So, we will see what we are going to do with lambda. Okay. So, okay, maybe I will finish that and then come back to the full algorithm. Okay. So, fine, yeah. So, we saw that in the minimization step we have xk, which is the x that minimizes L gamma of x comma lambda for a fixed gamma and fixed lambda. The first question possibly is what is that value of fixed gamma and fixed lambda, right. So, okay, we will push gamma for a discussion a little later, okay. But for lambda, let me tell you the following. I mean, so you might have realized this by now. Okay. Suppose I know the value of lambda. So, I have already told you that the critical point of this problem, whatever I have defined here, min f of x subject to hj of x equal to 0, can be found by differentiating f of x plus summation lambda j hj of x with respect to x and with respect to lambda and equating it to 0, right. So, assume that some genie has come and given us the right value of lambda. Okay, that is the lambda star that you would find by solving this, right. So, assume that the lambda star is given to you. What would you then do? You will just find this gradient with respect to x and be done with it, right. So, whichever x satisfies the gradient of L with respect to x equal to 0, that is the answer, right. So, suppose lambda star were known, okay, then minimizing the Lagrangian with respect to x. So, maybe I write it fully with respect to x gives us the critical points, right. So, that is what happens here as well. Suppose some genie comes and gives us the value of lambda star. Okay. So, then we just have to, I mean it turns out that x star is just argmin x in Rn L gamma of x comma lambda star, okay, for any gamma positive. Okay. So, good. So, but we do not know the value of lambda star. So, what do we do? What we do is we actually start with some particular value of lambda, okay, and update it iteratively. So, like how we update x. So, we start with some x 0 and then keep updating it to x 1, x 2, x 3, so on by solving a minimization problem, right. So, in a similar way we update the value of lambda as well. So, how do we do that? I mean, what is that particular update step of lambda? So, that is simple as well. So, recall that. So, yeah, from this step we have del f of x plus summation lambda j del height j of x equal to 0. So, that is from the analytical solution. Okay. And when you consider the augmented Lagrangian method, the equation is here. Now, what does this give us? Del L gamma of x lambda equal to 0. So, this actually gives us del f of x plus summation lambda j plus 2 gamma h j of x into del h j of x equal to 0. Yeah, so this is from j equal to 1 to m. Okay. So, for each del h j of x, you can see what you are getting to replace the lambda j that you have here. Okay. So, this is going to be our update step. In other words, we will initialize lambda 0 and we update lambda 1 equal to lambda naught plus 2 gamma h of x. So, h of x is a vector which consists of m elements in the vector, right. So, if you are asking how did you get this, I got it from here. So, I have lambda j plus 2 gamma h j of x, right. So, yeah, if you consider this as a vector, it is lambda plus 2 gamma h of x, and that is what I have here. Okay. And in general also we update lambda k plus 1 equals lambda k plus 2 gamma h of x. Okay. And we do not update gamma. So, we just retain the value of gamma whatever we had whatever we fix initially. Okay. So, now the full algorithm comes as follows. Okay. So, what is the algorithm? So, yeah, this is the algorithm for augmented Lagrangian method with when you have only equality constraints. So, you first initialize x 0 and yeah k equal to 0, the tolerance. So, some gamma positive and yeah, the new thing that comes here is you initialize lambda 0. So, recall that lambda 0 is actually a vector, lambda 0 1 to lambda 0 m. Okay. So, yeah, x 0 is also a vector, but that I think you know by the discussions for the first 7 weeks, right. So, of course, x 0 is a vector, k is 0 and tolerance gamma is some positive number, and you also initialize lambda 0 to some m dimensional vector. Okay. M is the number of constraints, if you could if you recall. Okay. Fine. And this is just a repetition of, so yeah, you now have a constraint while L gamma of x k lambda k minus f of x k greater than the tolerance. So, you find x k which is the arg min x in R n L gamma of x lambda k. Okay. Of course, you add k equal to k plus 1 and this can be found by any algorithm for unconstrained optimization, say gradient descent method, conjugate gradient or Newton method or quasi Newton methods. Okay. So, yeah, and you write k equal to k plus 1. There is one more step that is remaining, which is the update for lambda, right. So, you update lambda k plus 1 as, or maybe I should have written that step first. You write lambda k plus 1 equals lambda k plus 2 gamma h of x, and yeah, now you write it as k equal to k plus 1. Okay, so yeah, this is actually x k plus 1 I should have written. Yeah, okay, and yeah, so when you actually satisfy this particular constraint, you write the output. Yeah, output x star equal to x k, and actually I should write x star lambda star equal to x k lambda k. Okay, because yeah, in case you I mean when we actually solve an optimization problem, a constraint optimization problem, we do not just write x star as the critical point, we give x star lambda star as the pair of critical points that are required, right. So, augmented Lagrangian method actually gives us the x star as well as lambda star, and quadratic penalty method does not. Okay. So, that is something to be remembered as well. So, you can actually see that at least when you have only equality constraints, right, the algorithm for quadratic penalty method and augmented Lagrangian method remains almost the same, right. So, yeah, if you compare what you have here and compare what you have there, even the steps you can see that they are exactly the same, right. The initialization has a little bit of difference. Instead of initializing the gamma, the set of gammas, you initialize one value of gamma and a lambda vector, and yeah, these remain the same as well. You just updated the value of lambda and the output, right. So, in fact, I mean understanding augmented Lagrangian method when you actually know quadratic penalty method is quite simple. I will briefly let you know what the differences are, so that yeah, it is completely clear how you come from quadratic penalty method to augmented Lagrangian method. Okay. So, yeah, in quadratic penalty method you had q of sorry, I will start from initialization. Okay. Maybe I can write it down in the form of a table. So, this is quadratic penalty method and this is augmented Lagrangian method. Okay. So, the first step is in initialization, okay, right. So, here you initialize a sequence of gammas, right, gamma naught, gamma 1 dot dot dot, which diverges to infinity, and yeah, so here it is yeah, so you only initialize one gamma and a lambda vector instead. The other initializations are same, x0, k, tolerance, they are all the same. Okay. And the second yeah, I think the function is different. So, here we minimize q of x comma lambda x comma gamma with respect to x. So, WRT is with respect to, if you are wondering what it is, and here we minimize L gamma of x comma lambda with respect to x, of course, and so the update of gamma, right. So, update of gamma happens via the sequence gamma naught, gamma 1 dot dot dot. Okay. So, yeah, maybe here I should have referred this as h x k plus 1. Okay. So, we have found x k plus 1 here. So, that is what you update lambda k plus 1 with. Okay. So, yeah, so but here update of lambda is via this equation lambda k plus 1 equals lambda k plus 2 gamma h of x k plus 1 and no update of gamma. Okay. But otherwise the procedure is quite the same. Okay. So, it is you can say so nicely poised between these two methods, the quadratic penalty method and augmented Lagrangian method. Okay. And the most important thing that we need to mention is that the two issues that I mentioned for quadratic penalty method, right. So, for high values of gamma, that is not going to occur here. You will see that for even very low values of gamma, I mean values such as gamma equal to 1, gamma equal to 10, right. So, even for such low values of gamma, right. So, we can actually converge to the solution in augmented Lagrangian method, and lambda will be the actual value of lambda that you will get when you analytically solve the problem min x min f of x subject to h j of x equal to 0 for all j equal to 1 to m, right. So, that is neither the value of gamma nor the value of lambda actually blows up, right. So, I mean they are the normal values that you see in practice. Okay. And the other issue that I had mentioned at the end of the previous lecture, week 7 lecture number 5. So, you had this weird example, I mean this is not only one example, I just gave a simple example where for certain values of gamma, positive gamma of course, the minimum actually diverges to minus infinity, right. I mean you do not converge to the minimum, and the minimum actually exists, x 1 star is equal to 0 and x 2 star equal to 2, because I mean that is already mentioned here, right. So, when you have the minimum 0 comma 2, but the minimum actually diverges to minus infinity, right. Such issues do not happen as far as augmented Lagrangian method is concerned. Okay. So, we will see an example possibly we will start with an example in the next lecture when, for equality constraints alone. Thank you.